Chemistry is awesome.
Right, Assalamualaikum warahmatullahi wabarakatuh and Salam Sejahtera. So welcome back to this channel. So how you doing, guys? Feeling good? Great. Alright, so in today's lesson I'm going to start with this. So what is this, guys? Yes, this is an Oreo sandwich cookie. Okay, Oreo sandwich cookie, and everybody knows, Oreo sandwich cookies consists of, we have two pieces of Oreo chocolate cookies, okay, and inside here, okay, and this white thing here is the vanilla flavored cream. Okay, so means that if we have two pieces of Oreo chocolate cookies and in the middle here, okay, the vanilla flavored cream, and we are going to get one Oreo sandwich cookie. Okay, but what if, guys, what if we have this chocolate cookies? Okay, so let's count this chocolate cookies together. So we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 pieces of Oreo chocolate cookies, and we have right, okay, so we have 1, 2, 3, okay, pieces of the vanilla flavored cream. All right, so right now what do we have here? Okay, so we have, right, 8 pieces of Oreo cookies, chocolate cookies, okay, and then we have 3 pieces of the vanilla flavored cream. Okay, guys, so if we are based on these quantities, okay, these quantities, how many of this Oreo sandwich cookies can be made? Okay, can be made out of this 8 pieces of Oreo cookies and 3 pieces of the vanilla flavored cream. Right, so let's check together. Okay, so if we have 8 pieces, 1, 2, 3, 4, 5, 6, 7, 8 pieces of this vanilla flavor, it's not vanilla, 8 pieces of this Oreo chocolate cookies. So based on these quantities here, we should have or we can make 8, means we can make, yes, we can make out of these 8 quantities, 8 chocolate cookies, we can make, yes, 4 sets, right, or 4 Oreo sandwich cookies. Okay, 4, okay, 4, and that is the quantity of Oreo cookies that we should make if we have 8 pieces of this. While if we have just 3 pieces of this vanilla flavored creams, okay, we can only make how many Oreo sandwich cookies? Yes, we can make 3 Oreo sandwich cookies out of these 3 pieces of vanilla flavored cream. Okay, so let's do this on the camera. Okay, so we have 1, okay, and then we put the cream here, right, and then we put the another pieces on top of it. Okay, guys, see, we have 1 Oreo sandwich cookies. Okay, 1. All right. Next, another. Okay, cookie, cream, right, put on top of it, and then, okay, right, see, we have the second Oreo sandwich cookie. All right, okay, and then the third cream means that we can make the third, okay, Oreo sandwich cookies. Okay, so the chocolate cookie, right, and then the cream. Okay, right, and then we have the cookie here. Okay, so we have the third Oreo sandwich cookie. Okay, so if you look in this green plate here, right, so we still have remaining 2 pieces of Oreo sandwich chocolate, 2 pieces of Oreo chocolate cookies. But why can't we make the fourth or the next set of sandwich cookies? Why? The question is, why can't we make another or the fourth set of Oreo sandwich cookies? What's the reason? Yes, because we do not have enough. See, we do not have enough vanilla flavored cream. Okay, so what can we tell based on these observation? Okay, what can we tell about this situation here? Okay, so means that right now these 2 pieces of Oreo cookies would be the excess items. Yes, it is called the excess item. So even though initially we have 8 pieces of this, so means that 8 pieces of this Oreo chocolate cookies, we should remember, we should make 4 Oreo sandwich cookies. But since we don't have enough vanilla flavored cream, because we only had just 3 of them, okay, 3 of the vanilla flavored cream, so that makes the quantities of the Oreo sandwich cookies that can be made out of this 8 pieces of Oreo chocolate cookies, okay, are just 3 cookies. Okay, we can only make 3 Oreo sandwich cookies. And why? Because the vanilla flavored cream is the limiting items. Okay, so that is what we call limiting items. Okay, so what is limiting items? So limiting items are, we can say that limiting items are the items which is completely used up. Okay, completely used up, okay, or finish first, okay, and what else? These limiting items limits the quantity of the final product form or final products produced. For example, since we have 3 vanilla flavored creams, so that's why we can only make 3 Oreo sandwich cookies, even though we have 8 pieces of this Oreo chocolate cookies. Got it, guys? Okay, so that is the concept of limiting and excess items. Okay, limiting and excess items. Alright, guys. So next, what we are going to do with these 3 Oreo cookie sandwiches. Okay, 1, 2, 3. So let's eat them up and see how delicious they are.
12 seconds later.
Alhamdulillah, those Oreo sandwich cookies were delicioso. Very, very delicious. Okay, enough with the cookies. Enough with the Oreos. Alright, so now let's move on. Right, so let's say, guys, let's say we have this reaction. Okay, and this is a balanced reaction, balanced equation. Okay, from this balanced equation, what can we say? Okay, so we can say that 1 mole of hydrogen reacts with 1 mole of fluorine to produce 2 moles of hydrogen fluoride. Okay, so means that if we have 1 mole hydrogen, 1 mole of fluorine, we are going to get 2 moles of hydrogen fluoride. So this is based on the stoichiometrical relationship in this reaction. So means that if you have 1 mole of hydrogen, you have 1 mole of fluorine, and the reaction will be completed. And we are going to get 2 moles of hydrogen fluoride and no more reactants left. Okay, so we are what happened to hydrogen and fluorine? So both of these hydrogen and fluorine were completely reacted. So no more. So that's why no more reactants left. Okay. However, what if we started this reaction? Okay. Not with 1 mole of hydrogen and not with 1 mole of fluorine. Instead, we are going to start this reaction with 2 moles of hydrogen and 3 moles of fluorine. How many moles of hydrogen fluoride shall we get? Okay. Right. So now let's look at how to solve for this problem. Okay. Right. Okay, so from this balance equation, okay, we knew that 1 mole of hydrogen reacts with 1 mole of fluorine to produce 2 moles of hydrogen fluoride. But we started the reaction with 2 moles of hydrogen and 3 moles of fluorine. Okay, guys. So in this case, actually you have the option here. Okay, you have the option here. You want to start with hydrogen or you can start with fluorine. So let's say I'm going to start this reaction with hydrogen, these moles of hydrogen. Okay, so if we have 2 moles of hydrogen, okay, so therefore, remember 1 mole of hydrogen should react with 1 mole of fluorine. Okay, but in this case, we have 2 moles of hydrogen. So therefore, 2 moles of hydrogen should react with 2 moles of fluorine. Okay, got it? Okay. Right. So what can we say here? So the moles of fluorine needed is 2 moles. However, okay, how many moles of fluorine we have? We have 3 moles of fluorine, or we can also say the moles of fluorine available is 3 mole. So if we compare between the moles of fluorine needed and the moles of fluorine available, okay, so what can we say? Yes, okay, so moles of fluorine needed in the reaction is less than moles of fluorine available. See, the moles of fluorine needed is 2 mole. Okay, but the moles of fluorine available is 3 moles. So that's why moles of fluorine needed is less than moles of fluorine available. Or we can say moles of fluorine available is greater than moles of fluorine needed. So in this case, what can we say about fluorine? Yes, so fluorine is the excess reactant, while hydrogen is the limiting reactant. Okay, remember okay, the moles of fluorine, since it is less than available, so that's why at the end of the reaction, okay, so fluorine becomes excess reactant while hydrogen is completely reacted, since hydrogen is the limiting reactant. Or okay, so let's say if you don't want to write it this way, actually there is another option. Okay, just now we started with hydrogen gas. Okay, with hydrogen gas, so why not we started the equation with fluorine? Okay, so let's say we have 3 moles of fluorine. Okay, so 3 moles of fluorine should react with 3 moles of hydrogen, because the ratio of the hydrogen to fluorine in the balance equation is 1:1. So it means that if we have 3 moles of fluorine, for the reaction to be completed, okay, so 3 moles of hydrogen must react with 3 moles of fluorine. However, we don't have 3 moles of hydrogen. So how many moles of hydrogen we have? Yes, guys, we have 2 moles of hydrogen, not 3 moles of hydrogen. So means that moles of hydrogen needed is greater than moles of hydrogen available. Okay, so this means hydrogen is not enough. Hydrogen is not enough. So what will happen to the reaction? Okay, so once the reaction occurs, okay, so this hydrogen will completely consume first, or use up first, while fluorine will become the excess. Okay, will become the excess reactant. So in this case, so that's why, okay, same as the previous just now, we are going to get hydrogen is the limiting reactant, while fluorine is the excess reactant. Okay, see? Alright. Okay, so what can we say about limiting reactant, guys? So limiting reactant is defined as reactant that is completely consumed, or we can say that limiting reactant is the reactant that is used up first in a chemical reaction and limits the amount of products formed. Okay, so that this is the definition of limiting reactant. Remember, okay, it is a reactant which is completely consumed in a chemical reaction. Okay, and one more thing, this limiting reactant limits the amount of products formed. All right. Okay, and then we are going to calculate. We are going to calculate how many moles of hydrogen fluoride shall we get from this reaction. Okay, if we have okay, 2 moles of hydrogen and 3 moles of fluorine just now. Okay, right, so since hydrogen is the limiting reactant, remember the definition of a limiting reactant: reactant which is completely consumed in a chemical reaction and limits the amount of products formed. So that's why in this case, since hydrogen is the limiting reactant, okay, so that's why this hydrogen limits, it shall limit the amounts of hydrogen fluoride formed. Remember the Oreo cookies, okay, so even though we have 8 pieces of Oreo cookies, okay, we should get how many? Yes, we should get 4 sets of 4 Oreo sandwich cookies. But since we only have 3 vanilla flavored creams, okay, so that's why we can only make 3 sets, 3 sets of Oreo sandwich cookies, because the vanilla flavored cream is the limiting reactant. Okay, limiting, so that's why we can only get 3 sets of Oreo sandwich cookies, and not 4 sets of Oreo sandwich cookies. Okay, so let's get back to this hydrogen and hydrogen fluoride. Okay, so from the balance equation, okay, so we know that 1 mole of hydrogen produces 2 moles of HF, or hydrogen fluoride. Therefore, if we have 2 moles of hydrogen, okay, so 2 moles of hydrogen shall produce 4 moles of hydrogen fluoride. Okay, 4 moles of hydrogen fluoride, because we have 2 moles of hydrogen, and this hydrogen limits the amount of hydrogen fluoride formed. So therefore, moles of hydrogen fluoride produced in this reaction is 4 moles. Okay, 4 moles. Okay, and then let's say, guys, okay, let's say what if we want to know, okay, if we want to know the mass of hydrogen fluoride produced. Okay, so just now we have already determined, okay, the moles of hydrogen fluoride produced in the reaction, which is 4 moles. Okay, and to calculate the mass of this hydrogen fluoride produced, we are going to use the molar mass of hydrogen fluoride, which is 20.01 grams per mole. Okay, and from this molar mass, okay, we knew that 1 mole of hydrogen fluoride weighs 20.01 grams. Okay, 20.01 grams. But we don't have 1 mole of hydrogen fluoride. Instead, we have 4 moles of hydrogen fluoride. So therefore, 4 moles of hydrogen fluoride should weigh. So if we calculate this, so what is the answer? So we are going to get the mass of hydrogen fluoride produced in this reaction is 80.04 grams. Okay. So this is the case if we want to know what is the mass of the hydrogen fluoride produced in this reaction. Alright guys, okay, so what we did just now, alright, we are trying to determine the limiting reactant between hydrogen and fluorine. So which reactant is the limiting reactant through a method, okay, by comparing reactant with reactant. Okay, so what we did was we are comparing the moles of reactant needed and moles of reactant available. So let's say if needed, okay, is greater than available, okay, so means that, okay, the reactant is the limiting reactant. Okay, but if the moles of reactant needed in the reaction is less than available, okay, so means that this reactant will become the excess reactant. So actually that is the first option, that is the option number 1. Okay, so actually another option that we can use to solve for this in order for us to determine so which reactant is going to be the limiting reactant. Okay, so you have a second option actually. So in this second option, what we are going to do, we are comparing reactant with product. Okay, so so even though there are 2 options, okay, 2 options here, you can use either one of this, okay, either one of these options. Okay, so in this second option, we are going to compare which reactant, okay, which reactant in the reaction produces less product. Okay, so the one that produces less product means that reactant will become the limiting reactant. So now let's look at this. Still, I'm going to use the same example here. Okay, so from this equation, we know that 1 mole of hydrogen produces 2 moles of hydrogen fluoride, and 1 mole of fluorine also produces 2 moles of hydrogen fluoride. And remember guys, okay, we have 2 moles of hydrogen and 3 moles of fluorine. Okay, so therefore, if we have 2 moles of hydrogen gas, so it should produce 4 moles of hydrogen fluoride, while if we have 3 moles of fluorine, it should produce 6 moles of hydrogen fluoride. So by comparing these two, okay, so we can clearly see here, okay, hydrogen produces less HF. Hydrogen produces less hydrogen fluoride, less product compared to fluorine. Okay, so in this case, okay, since hydrogen produce less hydrogen fluoride, or we can say produce less product than fluorine, and that makes hydrogen is the limiting reactant while fluorine is the excess reactant. So this is the method, guys. So this is another method, the second method to determine limiting reactant, but this time it is based on which reactant produce less product. to the one that produce less product. So this reactant will become the limiting reactant. Okay, so this is the second option.
Right. So next is let's look at this question here. And actually guys, so this is your tutorial question, okay, tutorial 1.3, question number 4. Okay, so you can check this question in your tutorial book. Okay, right, so now let's look at the question. Alright, so let's say we have a, what do we have here? So we have a reaction between 7 grams of copper 2 oxide, okay, this is the molecular formula CuO, and 50 ml of 0.2 molar nitric acid produces copper 2 nitrate and water. Okay, and the first question here, A, define limiting reactant. Okay, B, write a balanced chemical equation for the above reaction, and then determine the limiting reactant. Okay, now this is the one that we are discussing, okay, just now. And then calculate the expected mass of copper 2 nitrate formed, and lastly, determine the percentage yield if the actual mass of copper 2 nitrate obtained from the reaction is 0.85 grams. Okay, so later we will discuss on this, what is the percentage yield. So let's solve for A to D first. Alright.
Okay, so once again, what is the definition of limiting reactant, guys? Okay, the definition. Okay, rest. So limiting reactant is defined as reactant that is completely consumed or used up first, or we can say that finish completely in the reaction, okay, in a chemical reaction. And that is the first definition. Remember, when we want to define this limiting reactant, there are 2 points here. So the first point is a reactant that is completely consumed in a chemical reaction, and the second point that you must state in your definition is this limiting reactant limits the amount of products formed. Okay, so these 2 points, okay, will be the definition of limiting reactant. Reactant that is completely consumed in a chemical reaction and limits the amount of products formed. Alright, okay, so let's move on to the next question, B. Right, so in B, you need to write a balanced chemical equation for the above reaction. Okay, so let's look back at the question. So we have copper 2 oxide reacts with nitric acid, produce copper 2 nitrate and water. Okay, so let's write the reactants first. So what are the 2 reactants? Okay, so we have copper 2 oxide and nitric acid, and later in this question we are going to determine, okay, between these two, copper 2 oxide and nitric acid, so which one of these 2 reactants will be the limiting reactant and which one is the excess reactant. Okay, but for this question we are just going to balance the equation first. Okay guys, remember, balancing equation is very important, because if you balance it wrong here, okay, you are going to have problem in the next question, okay, C and D. Okay, right, so we have the copper 2 oxide and nitric acid. When these 2 reacted, so we are going to get copper 2 nitrate and water, and this equation is not balanced. Okay, right, and as usual we are going to start with the most complex substance. So in this case, copper 2 nitrate is the complex substance. Okay, so there is 1 mole copper here, 1 mole copper here. Okay, balance. And then nitrogen, there are 2 moles of nitrogen in copper 2 nitrate. But if we look at nitric acid, there is only 1 mole of nitrogen in nitric acid. So that's why nitric acid, moles of nitric acid, we must multiply by 2, okay, to balance the number of moles of nitrogen in this nitric acid. Okay, and then oxygen, there are 3 times 2, so there are 6 moles of oxygen here. Okay, so 6 moles of oxygen here, and then 6 mole of oxygen in nitric acid, and 1 mole of oxygen in water and 1 mole of oxygen here. Okay, and then hydrogen, there are 2 moles of hydrogen in water and 2 moles of hydrogen in nitric acid. So the equation is balanced. Okay, it's balanced. All right. Okay, so now let's move on to the question, to the next question. Question C. Okay, this time we are going to determine the limiting reactant. Okay, guys. But for this question, since we have just now we have 2 options, remember we have 2 options to solve for this limiting reactant, but in this question I'm going to use the first option. Okay, the first option, which is we are going to compare, okay, reactant and reactant. Okay, we are going to have a look at we are going to compare moles of reactant needed and moles of reactant available, okay, in the reaction. Okay, so first thing first, so in this reaction there are 2 reactants, and there were 2 reactants. Okay, so we have copper oxide and nitric acid. So first thing that you need to do is we need to determine how many moles of copper oxide and how many moles of nitric acid used in this reaction. Okay, used in this reaction. Okay, so since we were given just the mass of copper to oxide, which is 7 grams, okay, so we are going to calculate the moles of this copper to oxide, okay, using the mass given, and also we need to use the molar mass of copper to oxide, which is 79.545 grams per mole. Okay, so this is the molar mass of copper to oxide. Okay, so from here we are going to calculate moles of copper to oxide. Okay, so mass of copper to oxide divided by molar mass of copper to oxide. So therefore we are substitute the value 7 grams divided by 79.545 grams per mole, and we are going to get 0.088 moles of copper to oxide. Okay, and keep in mind guys, so this is the moles of copper to oxide that we use in this reaction. Okay, so we put aside this copper to oxide. Next, we are going to determine how many moles of nitric acid used in this reaction. Okay, so since nitric acid here is in the form of solution, okay, so we are going to use the molarity given and the volume given, okay, to determine its mole. Okay, so using the formula, moles of nitric acid equals to molarity of nitric acid, okay, multiply with the volume of nitric acid. So we are going to get 0.2 mole per liter times 0.05 liters, and this is the moles of nitric acid used in the reaction, 0.01 mole. Okay, right. Okay, so now we have the 2 moles. Okay, we have the 2 number of moles. We have moles of nitric acid and moles of copper to oxide used in this reaction. All right, so next is we are going to determine, so which one of these 2, okay, which one of these 2 will become the limiting and which one is the excess reactant. Okay, so based on the balance equation from what we did in question A just now. Okay, so here I'm going to start with copper to oxide. Actually, if you don't want to start with copper to oxide, you can also use nitric acid. At the end, still at the end of the day, we are going to get the same answer. Okay, but for this question, I'm going to use copper to oxide as the starting reactant. Okay, so from the balance equation, 1 mole of copper to oxide reacts with 2 moles of nitric acid. Okay, and we don't have 1 mole of copper to oxide. So how many moles of copper to oxide that we use in this reaction? Yes, here guys, 0.088 moles of copper to oxide. So therefore, if we are just using 0.088 moles of copper to oxide, so this copper to oxide should react with 0.176 moles of nitric acid. Why? Because the ratio is 1 to 2. Okay, so that's why this is the moles of nitric acid needed to react with 0.088 moles of copper to oxide. And do we have this amount of mole of nitric acid? So now let's look back at the moles of nitric acid that we have. Okay, so we have 0.01 mole of nitric acid, and this is the moles of nitric acid needed to react with 0.088 moles of copper to oxide. Okay, so moles of nitric acid needed is 0.176 mole, but we only have, or we can say the moles of nitric acid available is just 0.01 mole. So if we compare these two, okay, we are comparing these two, okay, moles of nitric acid available is less than moles of nitric acid needed. So what does this means to you? Yes, so this means nitric acid is not enough to react with 0.088 moles of copper to oxide. So what can we say about this nitric acid? Yes, so nitric acid is the limiting reactant. Or we can say that copper to oxide is the excess reactant. Okay guys, so clear? Alright, good. Okay, next. Right, so next is we want to determine the mass of copper to nitrate formed in this reaction. So since copper to nitrate is the product here, and remember in the definition of limiting reactant, okay, reactant which is completely consumed in a chemical reaction. And remember the second point in the definition of limiting reactant, what is it? Yes, it limits the amount of products formed. So that's why in this question D here, in order for us to determine the mass of copper to nitrate, so we need to use the moles of nitric acid, okay, used in the reaction. Why? Because nitric acid is the limiting reactant. So that's why the quantity or the moles or the mass of this copper nitrate, okay, greatly depends on the mole of this limiting reactant, which is nitric acid. Okay guys, so now let's look at how to solve this problem. Okay, so once again, since we knew that or we have determined that nitric acid is actually the limiting reactant, so this nitric acid will limit the amount of copper to nitrate formed in this reaction. Okay, so from the balance equation, okay, so we knew that 2 moles of nitric acid here produce 1 mole of copper to nitrate, but we don't have 2 moles of nitric acid in this reaction. We only use 0.01 mole of nitric acid, so therefore it should produce 0.005 moles of copper to nitrate. And this is the moles of copper to nitrate, okay, produced in this reaction. Okay, produced in this reaction. Right. Okay. And then we are going to determine the mass of this copper to nitrate produced in this reaction. Okay guys, alright, so we are going to use the molar mass of copper to nitrate, which is 187.56 grams per mole, right? Okay, so mass of copper to nitrate, right, equals to moles of copper to nitrate times molar mass of copper to nitrate. Okay, so 0.005 moles times 187.56 grams per mole, and we are going to get 0.9378 grams of copper to nitrate. Okay guys, so that is the mass, and that is the mass of copper to nitrate produced in this reaction.
Ladies and gentlemen, we have come to the last question of the day. Alright, question E. Determine the percentage yield if the actual mass of copper to nitrate obtained from the reaction is 0.85 grams.
Alright guys, okay. Before we can calculate the percentage yield, I think it's better let me explain to you. There are two terms first. So the first is theoretical yield. Right. So what is theoretical yield? Or in BM we call it as hasil theory. Yes, hasil theory. Theoretical yield. Okay. So theoretical yield is defined as the amount of product that would result if all the limiting reactant reacted. Okay, for example, let's use this equation once again. Okay, the problem that we are discussing right now. Okay, so from the balance equation, we know that 1 mole of copper 2 oxide reacts with 2 moles of nitric acid to produce 1 mole of copper 2 nitrate and 1 mole of water. Okay, but in this reaction, we have 7 grams of copper 2 oxide, or in the form of moles, we have 0.088 moles of copper 2 oxide. And this amount of copper 2 oxide reacted with 0.01 mole of nitric acid, or 50 mils of 0.2 molar nitric acid, or if in the form of moles, we are going to get 0.01 mole. Okay, so just now we have already determined in this reaction, nitric acid is the limiting reactant, and that's why the moles of copper nitrate, okay, should be produced in this reaction will be, or we can say that it depends, okay, on the moles of nitric acid. So that's why if the mole of nitric acid in this reaction is 0.01 mole, so theoretically, we are going to get 0.005 moles of copper to nitrate, or in the form of masses, it is 0.9378 grams of copper to nitrate produced in this reaction. Okay, and this yield here, so that is what we call as theoretical yield. Okay, theoretical yield. So what is theoretical yield? Remember, so theoretical yield is the amount of product that would result if all the limiting reactant reacted. And remember guys, okay, so this theoretical yield of product is always determined or calculated from the balance equation. Okay, from the balance equation, and that is theoretical yield. Okay. Right, so next is the actual yield or hasil sebenar. And just now is theoretical yield, hasil teori, and this time is actual yield, hasil sebenar. So what is actual yield? What is actual yield? So actual yield is defined as the amount of product actually obtained from a reaction. Okay, from a reaction. Okay, for example, okay, based on the theoretical yield just now, okay, if we have 7 grams of nitric acid, okay, or if we have if we have 0.088 moles of copper to oxide, okay, and 0.01 mole of nitric acid, so therefore the amount of copper nitrate, okay, that was produced in this reaction should be 0.005 moles or 0.9378 grams. Okay, the mass of copper to nitrate produced in this reaction, and this is the theoretical yield. So however, okay, in the actual reaction, okay, we don't get this 0.9378 grams that we should get, okay, for the mass of copper to nitrate. Instead, what we get is we only, okay, manage to get 0.85 grams. So this mass here, so this is what we call as actual yield. Okay, remember 0.9378 grams, that is the mass of copper nitrate that we should get based on the moles of copper nitrate, moles of copper 2 oxide and moles of nitric acid that we have. Okay, so we have 0.088 moles of copper 2 oxide and 0.01 mole of nitric acid. We should get 0.9378 grams of copper to nitrate. However, in the actual reaction, so let's say we only manage to get 0.85 grams. And this yield here, so this is what we call the actual yield. Please keep in mind, in any chemical reaction, for example, let's use this reaction that we are discussing now. Okay, so suppose if we have copper 2 oxide reacts with 2 moles of nitric acid, yes, we should get copper to nitrate and water. Okay, so however, in the actual situation or in the actual reaction, sometimes a chemical reaction like this, such as this reaction, produces side products. Okay, side products. Okay, so that's why the amount of products that we should get, okay, will be different. Okay, will be different from what we actually get in this reaction, because of this reaction produce side products. And that is the case, and that is the case why we are going to have two different yields. So that's why the actual yield and the theoretical yield, okay, is different, okay, in terms of the values or the quantities. So now is the time to look at what is the percentage yield. Okay, percentage yield, right? So percentage yield, okay, is defined as the actual yield, right? So the actual yield divided by theoretical yield and times with 100%. Okay, and remember, the actual yield and this theoretical yield, it could be either in grams or moles. It could be in grams or moles. Okay, right. And one more thing, remember, the value of percentage yield is always less than 100%. Okay, less than 100%, unless the reaction is the same with theoretical. But normally in normal situation, we won't get percentage yield 100%. Normally it should be less than that. So that's why the percentage yield is normally the value is always less than 100%. Okay, so now let's look back at the question. Since we want to determine what is the percentage yield of this copper to nitrate. Okay, right. So remember, the theoretical yield was 0.9378 grams. Okay, so this is the theoretical yield, and this theoretical yield was determined, okay, through calculations, that we did in the previous question B and question C, right? And also question D, right? Okay, and then this 0.85 grams, the actual yield, and this was given in the question. Okay, so to calculate the percentage yield of copper to nitrate, so okay, we know that the actual yield divided by theoretical yield, okay, times 100%. Okay, so remember guys, so this actual yield and theoretical yield, you have two options, whether you want to use the moles or you want to use the grams. Okay, it is not necessary to use grams. Actually, we can also use moles. But in this case, I'm going to use the masses. The masses or in grams. Okay, so the actual yield is 0.85 grams. Okay, so divide by 0.9378 grams times 100%, and we are going to get, right, 90.64%. And that is, guys, and that is the percentage yield of copper to nitrate. It is just 90.64%. Okay, so that is how we calculate percentage yield. Alright guys, so let's summarize what you have learned in this lesson today. Okay, so the first part of this lesson, okay, you have learned on the definition of limiting reactant and also the definition of the percentage yield. Okay, and then we also have already discussed the question. In this question, you need to perform stoichiometric calculation using mole concept to determine the limiting reactant and to determine the excess reactant. And also, just now in the last question, we have also have a look at how to calculate percentage yield. Okay, so that's all for today's lesson. And in the next lesson, guys, we are going to enter Chapter 2 because we have already finished with Chapter 1, Matter. Okay, so in the next chapter, okay, we are going to enter the new or the second chapter of this chemistry SK015, which is atomic structure. Alright, so that's all for now. Thank you for watching, and I'll be seeing you again in the next video, inshallah. Bye bye.